In this video, we are going to look at polynomial graphs and see what the connections are between the equations and the graphs themselves. So first, we're going to look at these functions, and I've already graphed them on the graphing calculators. So what I'd like you to do is when I show you the graphs, I want you to draw a little sketch in your notes. So take some time. If you need to pause the video, please do that. Take some time to just draw a little sketch of these graphs so you can see what the shapes look like. And then here are the other two graphs. Okay, and what I want you to notice first of all is just the general shapes of polynomial graphs. They kind of look like roller coasters. So they go up and down and up and down, and this is what a general polynomial graph looks like. Now, they're all kind of different. All right, so how many, hills and valleys there are, that's different depending on what the equation is. And also whether we start with the graph going down like this. So if you notice that this one, if I put an arrow on it, it would be pointing down, and this one, if I put an arrow on it, it would be pointing up, right? Whereas this one, the one on the left is pointing up, and then this one, the one on the right is pointing down. Okay, so we call that end behavior, right? What's happening at the ends. And then in the middle, we've got all these, like I said, these hills and valleys, peaks and valleys that occur in between the ends. Okay, and then also too, we have these points, these graphs crossing the x-axis at various points as well. Okay, so what I want to look at, first of all, let me remind you, we said when we were doing quadratic, so like this one right here is a quadratic, it's a parabola. These x-intercepts are where we set the equation equal to 0 and we solved. And so that's what we did in the last video, is that we were solving polynomial equations. So that's when we solve those polynomial equations, those answers are where our graphs are going to cross the x-axis. So that's going to be helpful in linking the equations to the graphs themselves. Okay? So if I was looking at this graph, I would know that one of the answers is x equals 1, since it's crossing at x equals 1. And then this one, it looks like, I don't know, like negative 2.3 or something like that. So I would expect when I was solving this polynomial equation that I would get those two answers. Okay? So I'm just reminding you about that link between factoring, solving equations, and the x-intercepts. Okay, so the new thing that we haven't really talked about is, like we said, the end behavior, what's happening at the ends, and then how many hills and valleys do we have. Okay, so let's first look at the end behavior. So I'm going to put arrows on all of these graphs so we can really see which way are these pointing. Okay, so if you look up here at these, the end points are pointing in opposite directions. So the ones on top, okay, these are, the left is doing the opposite of what the right is doing. Whereas the ones down here on the bottom, the endpoints are doing the same thing. So the left is pointing down, the right is pointing down. Or here, the left is pointing up and the right is pointing up. So what I want you to notice now is what's similar about these two polynomials down here versus these two polynomials up here. So if you've had some time, and sometimes it's hard to find these patterns, but if you look at the degree, and remember we said degree is the highest power. Okay, so I'm going to focus your attention to the degree. Do you see how the degrees up top, the top two graphs, the degrees are odd numbers, they're 3 and 5. Okay, so these are odd up here. And then the degrees down here on the bottom two are even. Okay, so that's going to be helpful in determining whether the end behavior is going to be doing the same thing. So when they're even, they're doing the same thing. And we'll write a summary in just a minute. We'll organize all of this. And then when they're odd, they're going to be doing the opposite thing. the left and right will be doing the opposite. And that's kind of nice, O for odd and opposite. And the other thing I want you to notice is that if you look at the graphs on the left versus the graphs on the right, do you notice that the graphs on the right, their right in behavior is always up, and then the graphs on the left, their right in behavior is down. So I want to point out, let's figure out what do the ones on the left have in common and what do the ones on the right have in common. So now I'm going to focus your attention to the lead coefficients. Do you see that? And then here, remember, this lead coefficient is 1. So do you notice that the lead coefficients on the left, these are negative. So they're both negative. It doesn't matter that they're both -2, but they're both negative. And so when the lead coefficient is negative, then our right in behavior, our right arrow is going to be pointing down. All right, but over here, our lead coefficient is positive. And when the lead coefficient is positive, then the right arrow is going to be pointing up. So let's write all of that in our summary. Okay, so you've got a little chart in your notes that we're going to write all of this pattern, all these end behavior patterns in our summary here. So we were talking about the degree. And so we said if the degree is even, and remember we had 2 evens, right? We had a lead coefficient that was positive, one of them was positive. And then we had one where the lead coefficient was negative. And we said that it doesn't matter if they're even, then the right and left behavior are going to be doing the same thing. Okay? So these are going to be doing the same thing. Okay. And then when they were odd, we said that the left and right end behavior will be doing the opposite thing. So one will be going up, one will be going down. Okay. And then for the odd too, we had one of them was positive and one of them was negative. Okay. Now, then we said, well, the lead coefficient, whenever the lead coefficient was negative, then the right end behavior was going downward, right? And then whenever the lead coefficient was positive, then the right end behavior was going to go upward. Okay, so this is directly linked to the right end behavior. So in order to determine the left, we are going to use the green stuff, the degree, to determine what's going to happen. So we said in this first one, if it's even, then the right and left do the same. So if I know that my right end is going up, then my left will also be going up. And then on the second one, we said that if it's even, then they will do the same. And the right was going down, so that means the left will also be going down. Okay. Third line down, the lead coefficient was positive, so that meant that the right was going up. However, we had an odd degree, so the left is going to be doing the opposite. So since the right is going up, the left is going to go down in the opposite direction. Okay. And then the last one, our lead coefficient was negative, so right was going down. So the left is going to be going opposite again since it was odd, so that would be going up. So this works for any kind of polynomial as long as we look at the degrees and lead coefficients. So over here, we can write some examples. So I could have a polynomial that looks like this. With a lead coefficient and an even power, so I could have 3x to the 4th minus 5x, and the rest I'm just making up. So it could look like that. All right, for the next one, let's write an example where we have an even degree, but a negative lead coefficient. So I would have like maybe negative 5x to the 2nd power minus 3x. Okay. And so for the third example, I want to make sure my degree is odd and that the lead coefficient is positive. So let's say my lead coefficient is positive 7 and my degree is 3. Okay, so I'm just going to leave it like that. It doesn't have to have anything. It could, but it doesn't have to have anything added afterward. And then for an odd degree and negative lead coefficient, let's say this is negative 4 x to the 5th power plus 2x. Okay, so those are all examples of how the end behavior works. So now let's look at this. Let's use this pattern to help us identify the end behavior of these polynomials that were given. Okay, so in this one, number 8, the first thing we're going to look at is the lead coefficients. So the lead coefficient is negative. So remember, that means that the right end behavior is going to be going downward. And then if we look at the degree, the highest power, here, let me write that this was the lead coefficients. And so here where the degree was odd, 3 is odd, remember that all of the degrees are going to be positive. So if you're getting confused on whether the degree should be positive or negative or even or odd, they're always going to be, the powers are always going to be positive. So doing positive or negative for a degree doesn't really make sense. Okay, so for degrees, we're looking for whether they're odd or even. Okay, and we said if they're odd, remember the O's, odds are opposite. So that means that the left end behavior is going to do the opposite of what the right did, so it will be going upward. Okay, let's do one more. So in this number 9, my lead coefficient, I'm going to put LC. I'm going to abbreviate LC. My lead coefficient is positive 2, and remember we care that it's positive. Okay, I don't care what the actual number is, I just care that it's positive. So that means that my right end behavior is going to be going upward. And now I'm going to look at the degree. The degree is 5, and remember I care whether 5 is odd or even. Okay, so since it's odd, then the left is going to do the opposite of what the right's doing. So the left will be going down. Okay, so how does that help me with the graph? Well, I know that when I have all my hills and valleys and everything, the left is going to be going upward, the right is going to end up going downward, and then I'll have some kind of loops in the middle. Okay, over here it would be just the opposite. The left is going to end up going down, the right is going to end up going up, and then I'll have some loops and stuff in the middle. Okay, so that's one way to help us identify the graphs of polynomials. The other way is the turning points. And that's what I was talking about, the hills and the valleys. So when we want to talk about how many bumps do we have in the middle, okay, these are called turning points. And the number of turning points is at most, so this is very important, this word right here, at most, the turning point is 1 less than the degree. So for example, if I have a cubic function, all right, so y equals, let's say, x cubed minus 5x. Okay, so a cubic function can have 2 turning points at the most. So I could have it go like 1 and then 2. So you see how I have 1 hill and 1 valley. Okay, so that's 2 turning points. Okay, now I could have a cubic function if I just did y equals x cubed. This one doesn't have any turning points. It looks like this. Okay, so it doesn't have any hills or valleys. So I want to point out to you that when we say at most, it means that the most it can have is 2. It could have less. Okay, so here's another example. If I have a degree of 4, if there are 3 turning points, so let's say I'm looking at a graph, 1, 2, 3, So let's say I have 3 turning points, okay, 2 hills and 1 valley. Okay, so I have a total of 3. That means that the equation of this has to at least be x to the 4th or higher. Okay, it couldn't be x to the 3rd or x squared or anything like that. So I would have something like this, or I could have something like x to the 5th or x to the 6th and so on. I don't know, but all I know is that it has to be at least 4 or higher. Okay, so that's one way that we can help with how many bumps are in the middle. And then just some vocabulary. We have what we call a local maximum. That's just what we call those peaks of the hill, the top part of the turning points. So when I was calling this the top of the hill, those would be local maximums. Okay, so these are local maximums. Okay, and then we also have the term local minimum, and that's just a valley, all right? It's the bottom part of a turning point. So that would be a local minimum. All right, they just call it local because it's not really the lowest point of the whole entire graph. It's just meaning that it's just the bottom of a valley. Okay, so we're going to be doing a lot more with these graphs in class. So make sure to bring these notes and we will practice.